So are we ready to start, or shall we wait a few minutes? Okay, so good morning. And today we will, you actually have a tough morning. You had a tough morning already getting up earlier and having a quick breakfast. And we will also do a little bit quantum mechanics, and that's usually the hardest part. And nevertheless, I think it's worthwhile to do some quantum mechanics so that you at least know that after all, it's a doable thing. It's nothing that is sort of mysterious, but it's actually something that you can put a computer, and you can calculate, and you can compute your response to all kinds of pulse sequences. And that's the basics of understanding how to design experiments and how to analyze what is happening. And in fact, you will learn then also what type of information you can really get from doing NMR spectroscopy. So the fundamental, for the start of it, is actually that we look at coupled spin system, and this is where we stop. We look at two spins being coupled, and it could be the dipole-dipole interaction, or it could be the J-couple. And then we get the spectra that look like the spectrum underneath, and this is what you hopefully remember from the last lecture. If we have two spins, A and X, then they would have, without coupling, resonance frequency A giving one line, resonance frequency X giving another line. But when they couple, that line splits into two, and you get two lines, a doublet for A and a doublet for the spin X. And that means that there must be four energy levels, because we have, or at least four energy levels that give rise, so that we have these four lines, and then we have four differences between energies that correspond to the transition energy and to the resonance frequency. But we also have these zero and double quantum transitions in there. Now, of course, I could start and say, well, let's do the quantum mechanics for a spin system of two coupled spins, but that would take a lot longer than 45 minutes, what we have for today. So what I will introduce to you is just the quantum mechanics for a single spin. And the quantum mechanics for a single spin is sort of equivalent what we will do today, what Bloch has derived with the Bloch equations, or what Sommerfeld has derived for the precessing, for the spinning top, to understand precession and the mechanical motion of the spinning top, or you remember the rotating bicycle wheel, and Bloch has translated that into the magnetization precessing in a magnetic field, and now we will do the quantum mechanical analog for that. And so that leads us then to the description of how do we progress with or what type of mathematics do we need in order to move ahead by describing that. And you know the fundamental equation in quantum mechanics is the Schrödinger equation. I hope you pronounce it the way you pronounce it, but I pronounce it the way Schrödinger used to pronounce it. So his name was, he is actually from Austria, and he had a British mother and an Austrian father. So he was bilingual, English and German. So Schrödinger came up with a very crazy equation that it reports some energy balance of a quantum mechanical system, but it's very hard to really understand it analytically. And it's still a mystery to me how he ever could come up with writing his equation, but it works, and it helps us to understand the processes on the elementary level, on the quantum level. So we will not deal with the Schrödinger equation, but we will deal with an equation that is called the von Neumann equation. And that is an equation that relates to the density matrix. And the density matrix is sort of a fundamental quantity. It's, first of all, it's an odd name for you. It's a quantity that is very fundamental to understanding NMR. So everybody talks about the density matrix. And the density matrix is sort of what can be understood. Now it's a matrix, not a vector anymore, like a magnetization vector, except that now we have a matrix, and the matrix evolves with time, like a vector precesses around the magnetic field. The matrix evolves with time. And the very first thing I need to do is that I introduce to you what the density matrix means. I mean, we know already that the state of a spin can be described by a wave function. I hope all of you had some quantum mechanics that this is a concept that I can start with. Now the wave function is sort of a virtual concept. I've never really seen a wave function written out, that it is some functional form like sine x or something. Some people approximate it with exponentials or with wave packets, functions, but it's not really needed. The funny thing is one only needs expansion coefficients of the wave function. One usually says the wave function is the sum of many other functions. And the question is how much of any other function is in there. These are the expansion coefficients. So what one writes down is that the wave function, now I have to go to my first slide. The wave function of a general state of our coupled spin system, and I write that down here now for the two spins that are coupled, and then I'll go for a specific example looking only at one spin. If we look at the two spins and the wave function of any state of the spin, be it just at rest, parallel to the magnetic field, or anti-parallel, then the wave function would be simple. And now it's some state and some transition state. So it moves around somehow. And then the wave function, which we call psi, is the sum of a wave function where both spins point up, where one points up, one down, one up, and both point down. So we don't even say what that function looks like. We just say it's the sum of the bracket means the wave function A1, A2, A3 are coefficients, the amplitudes of that wave function. They tell us how big it is. And we may also write, instead of these arrows, we may call the wave function alpha alpha, alpha beta, or beta beta. That's a different notation that you very often find. Say spin state alpha is when the spin is up, and spin state beta is when the spin is down. And for two spins, of course, we have all these crazy combinations that you can have for the wave functions. That's for the states, and this is what these four wave functions mean. Or you call them psi 1, psi 2, psi 3, psi 4. That's a hard way to say it. And so there's some function. And what quantum mechanics tells us that what is really surprising, you don't need to know the wave function. You just need to know that they are also normal functions. Which means you multiply two with each other, psi 1, psi 2, and integrate over them, you get a 0. But if you multiply psi 1 with itself, then you get a 1, and you integrate over them. So that's all you need to know. So the orthonormality is one thing that is really that is important. And what we need to describe the state of the spin system is not that we need to know the wave functions. We need to know the expansion coefficients A1, A2, A3, A4, and not even those. We just need to know all the products of two coefficients. So what we really need to know is A1 times A1. This is star means the complex conjugate because they're complex number. X plus IY, the complex conjugate is X minus IY, so the I changes its sign when you form the complex conjugate. So this is actually the magnitude of the complex number A, so it's just A squared, A1 squared. So there are, of course, a set of combinations that one can arrange with the complex coefficients A1 times A1, A1 times A2, A1 times A3, A1 times A4. So you get a 4 by 4 matrix of all these expansion coefficients. Now that applies for one single spin, but we know that we have 10 to the 23 spins in there. So many. And we cannot observe each single spin, although now there are some experiments actually where you can observe single spins, which is a fascinating topic. And so if we have these 10 to the 23 spins, we can only observe the ensemble average. And ensemble means we take all the spins and we see if we average over all the spins, over all the numbers at a particular moment in time, then this is what we can measure. And this is why I put in the square bracket. It means it's the statistical average of what we see over all the spins. And this matrix is something where we can label the rows and columns now with the wave functions that I've noted in here with alpha, alpha, beta, alpha, alpha, beta, beta, beta. And they connect, let's say, an element in here. Let's go to this one here. Connects the state beta alpha, because this A2 refers to the state A2, A1 refers to the state beta alpha, and here it connects it at this position to the state alpha alpha. So two states of the spin system, two particular states of the spin system, are connected by that matrix element. So that actually means it is some transition. It is so the elements themselves along the diagonal, they describe the populations of the energy levels. So let's go back to the slide. For two spins, it's 4 by 4. If you have 10 to the 23, then ideally it would be gigantic. But of course, because you have 10 to the 23, you average only over the coupled spin pairs, and this reduces it. The 10 to the 23 is taken care of by the brackets over there. And so you only look at the two spins with the two different resonance frequencies. And say one is the spin, one is the first spin, it gives us the first alpha, and or this wave function. Of a single spin, that's the wave function of the second spin, first spin, second spin, and then we look at the pairs. We form the product, the new wave function of the pair is the product of the wave functions of the individual spins. So I probably didn't explain that nicely. We have the wave functions of the individual spins, the alpha and beta, and then you have all the combinations of wave functions of individual spins, giving us the wave functions for the coupled spin system. Remember, coupling, I explained, is always forming a product of two operators, or or two vectors. The spin vector coupled with spin vector 1, or alpha spin vector 1 couples with spin vector 2. Or the spin couples with the magnetic field. One vector couples with another. So the wave functions of a coupled spin system are the products then of the wave functions of the individual spins. And this is why we have two individual spins, and we have four combinations of their wave functions, which gives us four wave functions for the coupled spin. And to look at transitions, now these wave functions of the coupled spins, they would refer to, let's go back, the eigenstates, these states of the spin the energy levels of this four-level spin system. So we have these four wave functions, each of them refers to one of these states. Now if we want to look at transitions between them, then we actually have to have connections between two states. And that gives us a total of 4 by 4 combinations where we can have transitions. Okay. Now then we can look at how the magnetic quantum number would change if we go, let's say, that is the initial state in our energy level diagram, and this is the final state of our energy level diagram. Let's go back to the energy level diagram now. It would be helpful to have two screens. So let's look at a transition that goes from alpha alpha to beta alpha, or better, let's say, go for a transition that goes from beta alpha to beta beta. Let's take this transition. So that's our initial state, and beta beta is our final state. Yes. Yes. No, they're not in the same energy. That might have been gone by too fast. It looks like it's the same energy, and it is approximately the same energy. The energy difference between, let's say, from here to here, that is if your NMR spectrometer, proton spectrometer, is a 300 megahertz spectrometer, then it's H times nu, H times 300 megahertz is the energy difference from here to here. The energy difference between those two states is the J coupling. It's H times 10 hertz. So if you plot that on the graph, you would have 100 megahertz. That's 10 to the 8 versus 10 to the 1. And that you cannot see. You know, it's thinner than the line for the energy level that I've drawn.
That's why there are 4 lines, otherwise...
Well, there are 4 lines, and they're only separated by that little difference in the 2 energy levels. This is the difference between here. So the 4 lines are only the ones where the magnetic quantum number changes by 1, and that means one of the spin flips. Let's focus on these two, on the transition from beta alpha state to the beta beta state. And we flip one of the spins, we flip the alpha spin, and then it means it flips down, and then are both down, so only one of the spin changes, and that means the magnetic quantum number changes from 0 to -1, and that is then a single quantum transition, an observable transition. And they're observable because we put in a photon, a radio frequency quantum, and photons also have a spin 1. So all the changes we invoke by irradiating with photons invoke spins, changes of the quantum state by the quantum number by delta m equals 1. So that's why only these 4 transitions are observable. Let's take that transition. Alpha alpha goes to alpha beta. Again, the second spin, that spin here, changes from alpha to the beta state, and the first spin stays the same. While these 2 transitions over here, there is where the first spin changes from alpha to beta, from alpha to beta. So these 2 transitions are the transitions of spin A, and these 2 transitions are the transitions of spin B. And they are not the same because these 2 energy levels, although they appear to be at the same height, they're slightly offset. They're slightly different. If you go to lower and lower fields, then that shifts, then you would see how they sort of are being displaced because the total energy difference, the Zeeman energy, becomes smaller and smaller and smaller, and then you would see that difference. And that is why ultra-low field NMR, or you can even do zero field NMR, no applied magnetic field, no Zeeman interaction anymore, then that looks completely different, and that's a completely different coupling regime, very different quantum mechanics that one has to deal with, and but that's not the case of regular magnetic resonance. So we will stay with the high field approximation and that approach. It's probably a difficult enough issue to discuss. Yes. Well, this is what quantum mechanics tells us that it has a spin. It appears to spin. Well, spin is nothing that you can really observe in the sense that the formal quantum mechanics or description of the or understanding requires that the photon has a spin. But the classical interpretation would be that it spins around its own axis.
Which particle
if a particle doesn't have any charge, it still matters?
Yes, the neutron also has a spin. The proton has a spin and the neutron has a spin. That's why, a hydrogen has a spin 1/2, and deuterium has a spin 1. Due to the neutron. Okay. Now let's try to move forward here. But if you have questions, please ask, okay? Because this is a difficult topic. So we have these the transitions from one state to another, and these transitions from beta alpha to beta beta, we can express in the density matrix, so I have to go back to the density matrix. We go from beta alpha to beta beta. That would be, we go from that initial state to this final state. So these are where we start, and this is where we end up when we put in a photon or take out a photon from, or a radio frequency quantum from our spin system. Then we have to deal with that matrix element. So the part of the density matrix that describes the transitions from beta alpha to beta beta would be this density matrix element. Then we say this is a single quantum density matrix element because a change is responsible for a change of magnetic quantum number from alpha to beta, and that's delta m equals 1, and it requires one photon to do that. So it's a single quantum. One photon is equivalent to a quantum. So we do a single quantum transition. So that's why I put in here 1Q. 1 means a single quantum. Similarly, we can go, let's say, from alpha beta to, let's say, alpha alpha. Again, we change the magnetic quantum number of beta of the second spin from the state beta to the state alpha, and that element would also be a single quantum transition. And now let's go to a different one. Let's go from this element to this element, alpha alpha to beta beta. Both spins flip. So that's, now we need two photons. The magnetic quantum number, let's go to the energy level diagram again. Alpha alpha goes to beta beta. We go from here to here. And we need two photons to get there. It's a double quantum transition. Both spins need one quantum to flip. That's why I put in that description, I put the value 2Q on the corner. Because in either case, alpha alpha goes to beta beta, or beta beta goes to alpha alpha. Once two photons are absorbed, or two photons are emitted from the spin system. But there are also the other ones. There's beta alpha goes to alpha beta. So we have the spin state beta alpha goes to alpha beta. So one photon is absorbed, one is emitted. So it's still a two-photon process. But the total result is that the magnetic quantum number has changed by 0 in the net effect. And that we call a zero quantum transition. And then there are other elements. And there are elements that say that a state beta beta is connected to beta beta. Nothing changes. So when nothing changes, there is no transition. And what we actually look at is a single energy level, and that is and that density matrix element of that energy level that doesn't connect to, or the density matrix element that doesn't connect two states describes the number of spins in that energy state. It's just the population. How many spins? If you have 10 to the 23, roughly 1/4 is in each of the states. Probably fewer here than here. That's given by the Boltzmann distribution. About 1/4. And a little bit more maybe in that state, and a fourth and a little bit more less maybe in that state. So that's the population of the energy levels that is going on. So that's the density matrix. And the density matrix plays the same role as the Hamilton operator in the Schrödinger equation, in the so-called von Neumann equation, that was a Hungarian mathematician. Has a German name, but he was a Hungarian mathematician. And was a very clever guy, and he developed the math along with it. And that is an equivalent. You can actually derive the von Neumann equation from the Schrödinger equation, something I will not do. I'm afraid I have to sort of confront you with the von Neumann equation and say, this is what it is, but we will do one example and play with it. So that you know at least, even if you say, oh God, I can never repeat this, you can say at least, yeah, probably one can do that. And if I can do it, then probably my friend can do it. So at least you know that it is something workable, and not just something that's so mysterious that only some very smart brains understand. You can understand. I'm sure you can understand. But probably the time we are allowed to spend here will not suffice to get the detailed understanding. So what we've learned now is that the density matrix, which is simply the expansion coefficients of the general wave function for a two-spin system. The general wave function is the sum of the four product wave functions we need in order we get when we have two spins. We have four product wave functions: alpha, alpha, beta, alpha, alpha, beta, 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 and they have four coefficients, A1 to A4, and with these wave functions and these coefficients we can describe the general state of the two-spin system. And any transition in there is described by the density matrix, which collects the pairs of these expansion coefficients and the ensemble average, because we have, roughly 10 to the 23 or half of the 10 to the 23 spin pairs in our spin system to discuss. And because we have so many, we form the ensemble average, or we average over all spins. Now what is really a fascinating part of quantum mechanics, and I find it kind of ingenious, is the density matrix at time zero. So the wave function, let's say initially there's a density matrix in thermodynamic equilibrium. We know there's a magnetization in thermodynamic equilibrium. When you have enough, you put your sample into the magnet, and it takes 5T1 for the magnetization to align along the Z direction along the magnetic field. So that state is also described by a density matrix. It's sort of initial density matrix. And then you want to know what happens when you apply a radio frequency pulse. Then you change the density matrix, because you generate transverse magnetization from longitudinal magnetization. And then the magnetization starts to precess around the magnetic field. And again, the density matrix changes. The change of the density matrix is called evolution of the density matrix. Just a name, first of all, it's evolution, We evolve as time goes on. I get older every day. And so there's an evolution.
This combination is going to change. What is the evolution? This combination between 4x4.
It will always stay a 4x4 matrix, but the values in here, they will change. They're time dependent. Okay? So they depend on time. And the beauty of that is there is a time evolution operator. That means you apply an operator to the density matrix, and so I know that the density matrix now, let's say in thermodynamic equilibrium, and I apply the time evolution operator, and then I know what the density matrix looks like some time later. And some time later can mean right after the pulse, or after a certain evolution time when the magnetization frequency. So the concept of a time evolution operator is kind of cool, because it means you're sort of you are in one of the futuristic movies, and you apply a time evolution operator of 100 years, and you're suddenly 100 years in the future. And then there's an inverse time evolution operator which tells you, now let's go back. So you can jump back and forth in time in quantum mechanics. That's a cool concept. Unfortunately, there's sort of limitations which relate to relaxation in NMR. So you can't really do that. But for a single spin, you're able to do that. So what I've written down here is what the density matrix, this thing here, that is now I write as rho of t. Rho is a function of time, and I want to know the density matrix at some time t, and I can calculate it from the density matrix, knowing the density matrix at some time 0, t0, initial time. I know the density matrix in thermodynamic equilibrium. I want to know what does it look like. I know the magnetization when it's along the z-axis. I know that I apply a pulse, and I know it rotates. That is what I want to describe. I need the time evolution operator for my radio frequency constant. And that time evolution operator is u. It's called U, and it's called T minus T0 because it advances time from T0 to time T. And a matrix is usually transformed by multiplying from the left with the operator and from the right with the inverse operator. A matrix, that is something complicated, isn't it? So you multiply, if you want to transform a vector, you multiply the vector with a matrix. If you want to transform a matrix, you have to multiply from right and left with a matrix. From the left with the matrix and from the right with the inverse. So this is the operation of, let's say, this is the prescription now how to use the time evolution operator to calculate the density matrix from the density at time t from the density matrix you have initially. Let's take it as a recipe. So this is what you need to do in order to calculate it later. And then the question is, what does a time evolution operator look like? How do I know how to proceed? And the answer is written here. It's the Hamilton operator of the system. You say, now you replace Hamilton operator, time evolution operator, that's very confusing. Well, the Hamilton operator is just the energy, the operator that corresponds to the energy of the system. It is the quantum mechanical operator that corresponds to the energy. That is the Hamilton. Hamilton was a crazy man, by the way. That's a separate story. He wrote many books, and many of them were nonsense, but some were good. And so the good part is that, or sort of what is left with us is the Hamilton operator. And so there is an exponential function. It has an operator in the exponent. You know, what does it mean? You write an exponential function, but matrix in the exponent. And then the time. How do we work with the matrix and the exponent? It's a doable thing. We'll learn that. It's not very complicated, actually. So you can work with the exponential function and operator in the exponent as t minus t0. That's time evolution from the initial moment when you say, I know my density matrix, thermodynamic equilibrium, and then you go on and apply radio frequency, Pauli's evolution, etc. So that happens during the time t minus t0. You divide by h bar, this is a Planck's number. Planck's constant. Okay, so that's the density matrix, and that's the concept of the density matrix. And of course there are rules how to use the density matrix to then finally compute transverse magnetization. That's what you're interested in, because it's the quantity you measure. So you need to know how do I calculate transverse magnetization with the density matrix. And what I have in here, I see my time is running away much faster than I thought. I have only 2 slides for the 45 minutes. But here's an example of it's interesting, how the slide there's an example how we work with the density. The example says what is called from the density matrix of 2 spin couple, that is a 4x4 density matrix. That's well instead for a single spin. And a single spin only has 2 wave functions, one for the wave function being out, for the Eigen state being out, and the other one for the Eigen state being out. So we have to deal with 2 wave functions, which gives us a 4x4 density matrix. That's small. And that we have to plug in what the so-called von Neumann equation of motion of the density matrix. Von Neumann is the guy who produced that equation that replaces the Schrödinger equation. The Schrödinger equation, sort of is equivalent to the Bloch equation in our case. So this is the quantum mechanical formulation of the Bloch equation, where we want to understand coupled spins. If you don't think the single spin 1/2, you work with the Bloch equation. You're fine. That's simple. You can understand rotating vectors, recession, all this stuff we derive from the Bloch equation. You want to work with coupled spin systems. If you do your pulses, a 90-degree pulse, you have more than just vector spin. You have double quantum effects of these transitions, where the magnetic quantum has a change by 2 or by 0. Those you also need to describe. And to describe those you need to measure. And that's why this painful exercise of this morning is called atomy.
So the equation that gives us that is equivalent to the block equation is this one. The change, the time the derivative of the density matrix, is the derivative of a matrix. It's the commutator. What is the commutator? Thank you, that's awesome. So let me explain this. There we go. So the commutator of two matrices, so both of them are matrices, is matrix A times matrix B minus matrix A B times matrix A. This is just a shorthand notation for that discussion.
So there is a commutator in here. There's the square root of minus 1, I, minus I, divided by Planck's constant. And that would be equivalent to just a rotation of the density matrix for 3 seconds. And then there's an attenuation check. This is the relaxation check. There would be T1 and T2 effects, the relaxation of magnetisation towards thermodynamic equilibrium, except that now we have an operator in there that operates on the density matrix at time t minus the density matrix at time t0. So whatever difference of the density matrix in thermodynamic equilibrium is to the density matrix at time t, that has to disappear with time. If I wait long enough, I will get again the density matrix in thermodynamic equilibrium. Meaning, if I wait long enough with my sample in the magnet, eventually it will be in thermodynamic equilibrium. All the differences from thermodynamic equilibrium will vanish by T2 relaxation first, with transverse magnetization, and then by longitudinal relaxation with T1. So the difference of the density matrix at time t minus the density matrix in thermodynamic equilibrium will relax, and this is the relaxation super operator. And we call it the super operator and we can get more copies. So what we will do is we will consider the density matrix for the case that we will need next relaxation to simplify our life. Relaxation theory is again an issue which is very detailed and requires actually many models to understand. And it's important to understand material properties, but here we first of all need to understand how how we can deal with radio frequency pulses and precessions when we have coupled spins. But to avoid the complexity of coupled spins, let's just look at one spin. And we expect as a result, if we just want to apply one spin, one pulse, look at 3 precessions, and let's get the answer of what we get, what we expect from the block equations when we look at 3 precessions. That's the answer. So what we use are complicated formalism from calculate something you already know from the block equations, from applying a pulse, turning it over into the transverse space, and then see the linearization rotation. This is what I want to see when I use that formula. And that hopefully gives you some trust that, okay, if the formula does not work, it works for spin 1/2, and it probably also works for other spins that spin 1/2. So we take the evolution operator, that's written here, this is the Hamilton operator, and then we work for a single spin, we have to describe what are the matrix representations of the spin. And there are matrices that are describe the x component of the spin, the y component, and the z. So the spin actually is a spin vector, and the vector
has 3 components, phi x, phi y, phi z. That's a vector. That's easy. Now the problem that comes in here, each of them is a matrix. Okay, so it actually is a matrix that consists of and each of them has 4 elements.
What happens here? Oh. Okay, thank you. So each of them has 4 elements. This is a vector that has 3 matrices with 4 elements in each of its positions. It's a pretty complicated construction, but it's doable. You can apply all the calculus that you know to this, and you'll be able to figure that out rather quickly. And these matrices have been found by an ingenious scientist, Wolfgang Pauli, and they're called the Pauli spin matrix. And they're written down here. You find them in every textbook on elementary quantum mechanics. And this is the starting point to describe or to work with when you look at any coupled state, one half. And so that's one thing we need to know. And the second thing we need to know is what does our thermodynamic equilibrium density matrix do? Now, we know that in thermodynamic equilibrium, our Boltzmann magnetization is sort of an exponential function. And here and here we have the exponential function not of the energy divided by the energy of the spin system divided by the kV times T, Boltzmann constant times temperature. This is the thermal energy of room temperature. Or we have to take the Hamilton operator, which is again the energy. So we take the energy operator. Now again, it's a matrix that is in the exponent, and it's the Hamilton operator that we take here for this Riemann interaction. So the capital V, the interaction of the spin with the magnetic field. We have to take that Hamilton. And then we divide it by the time, that's just the normalization, and for the time being we say that this is 1 magnetic field. Now the question is, how do we compute this? And we have to figure out what is the Hamilton operator is here on the so that actually I have a long file here. We know that the Hamilton operator itself is proportional to the spin operator in that direction. It's a spin line along the z direction, and it's the product of the magnetic field and the magnetic moment in that direction. So, where am I? Now we have to figure out why actually it's written in here what the Hamilton operator is. It's the spin operator times the spin vector times the magnetic field, and the magnetic field is only in that direction. So the product of the two vectors only gives us the result of all of this. And we have the magnetic field, the paramagnetic field, which is R, and this is the operator, the vector component of the spin. So that's basically, this is what the energy operator for the two vectors. And now we have to know why is the density matrix when we have an exponent here. Why don't we say the density matrix is proportional to this rise? That is done easily because we know that we can expand the exponential function e to the minus x. We can write as 1 minus plus, let's say the plus is probably better, x plus, this is 1 over 1 bracket t, 1 over 2 bracket t x 0 plus 1 over 3 bracket t x u plus use that expression. We know that x is very small. And it is 10 to the minus 6 roughly at room temperature. So we can drop all these. Okay? So we know that
in this time, x is given by, it's basically the expression, it's x, and this is proportional to the reference frame as we got times the AX operator. So we know that rho 0 is proportional to AX because we are able to drop all the higher expansion terms from the exponent. So this is beautiful. We only have to deal with the Z operator of the density. So our rho 0 is the thermodynamic equilibrium density matrix. Our initial Z magnetization we start with finding out and then we plug it into the time evolution operator. And the time evolution operator for a pulse means that we apply a pulse in the y direction, that there is a rotation around the y-axis, which is why it's put in the density matrix for the angular momentum operator.
The matrix for the angular momentum operator in y direction. And this is the fifth angle. So the time evolution operator for the pulse is this operator, that function. And this would be the negative time evolution operator, the u to the minus 1.
U to the of t minus t0 for the pulse, and its inverse are this function. The y component represents the rotation of the, if you look at the Hamilton operator for the interaction of the spin with a magnetic field in the y direction, that's the precession around the y direction. The same as in the precession around the z direction, which is the vertical. Now we have the pulse, it's the one field along the y direction, so you have the y angular momentum operator. This is why the y angular momentum operator comes to be able to rotate. The rotation angular velocity. And if you do the precession around the z-axis of the z operator, there's a subsequent precession. Then your time evolution operator is what we get from here, that's after the pulse. We plug that in. And that actually produces IX, which you can calculate when you put the density matrix in here, and then you do that expansion of the exponential function, calculate all the different powers of these matrices, you will find you always get the same matrix. You can easily calculate. Beautiful. If you actually put the data right in, you will find that this is easy to calculate. You can do that. Because you can see the matrix multiplication of the matrix. And this gives you the precession. So you first see calculation of what happens after the pulse, then you plug that prime into the IX operator. So the result is really the result of the IX.
Is that matrix thermodynamic equilibrium into the transverse plane gives you the IX operator. By a rotation around the y-axis. Rotation around the y-axis. So it all comes out by putting in numbers, which you can do on paper sitting at home. Probably will take you a bit longer when you do it the first time. You do it the second time, you'll draw the class. And then you look at the free precession here, Clarice. The free precession means you take the x operator, now the magnetization is a transverse plane. And then you look at the precession of the transverse magnetization around the z-axis. And it gives you this. So you have the pulse, you have precession, and now you need detection. And detection is something that I haven't explained yet. The detection means you form the expectation value of the density matrix with the detection operator. And the detection operator is a coil, a radio frequency coil, which has a magnetic field in the, what do I have here, in the x direction. And that is represented again by the IX operator. So you have to form the trace of the density matrix with the detection operator, the trace of the detection matrix with the IX operator and the IY operator, at that particular time. And yes, the trace itself, what it means is you have two matrices, move this up. The trace of a matrix means the sum of the of these two diagonal elements. How do I do this? I probably should do that better. x1, 1, x1, 2, x2, 1, x2, 2. This would be just x1, 1 plus x2. It's the sum of the diagonal elements. This is what trace means. Then when you have the trace of the product of two matrices, you first have to form the product. That's the operation over all n, and then you form you sum up the diagonal. This is the sum over all n's. So this is something that, again, is a number that's easy to calculate. To come to a conclusion, we have to calculate the x and the y magnetization. So we have to take the expectation value for the x operator and the y operator. This is the x operator. This is the y operator. And the result of that, when you go through the calculation, is that you get a precession of the magnetization with the frequency omega 3. And that's exactly what you expect when you look at the Bloch equations, that your transverse magnetization, once you rotate the magnetization in the transverse plane, and the rotating frame rotates around the z-axis with the frequency omega 0. This is a very complicated way of calculating what the Bloch equations do. But it allows us to carry that over, make it a little bit more complicated, even to coupled spin systems. And that you can do not only for 2 coupled spins, with 3, 4, 5 coupled spins, and then work out, apply some more refined math to work out what complicated pulse sequences do, so that you know you could look at multi-quantum coherences, you could look at single quantum coherences, you collect the signal of particular chemical groups with particular J couplings, and design pulse sequences to look at particular elements of the density matrix, or to look at particular chemical groups, to transfer magnetization from hydrogen to nitrogen to carbon, and to look at all these effects. And the fundamentals of understanding these effects for coupled spin systems is the density matrix, that this type of math. So I know this was hard material for you in the morning. It was tough, and I hope at least you got a little bit of an idea.
And if you go away and say, well, this is so complicated, I will never do it, and this was not complicated at that job. And if you say, well, probably there's a way of doing it, in fact, I can do it myself, but at least I understand that other people can do it, then there's also a little bit of a benefit of doing that. But I think it's important to know that all the quantum mechanics, and spectroscopy is a quantum mechanical science, is durable, is describable, and the quantity in the individual resonance is the density. So with this, I think we can take a little break, and then assemble for solid state NMR spectrum.
Very short way of the cameras only, because retroactively we have to finish by 10 to the 5. Yes.
O matrix. O is just a matrix that says some operator. But the operator for detection is Ix for the X component of the magnetization, or Iy for the Y component. So replace O by Ix or Iy, which is done here. Now we have trace rho times Ix, trace rho times Iy. And that is the complex conjugate of the transpose of the matrix. It needs to be put into the right matrix.
Can you suggest any reference for this mathematics?
Oh yeah, there are plenty of books. I mean, the books I've mentioned in the beginning, I'm sure that Levitt has it in there. I have it in the books that I've written myself. Yeah, I would probably recommend Levitt. And the book that I've written, NMR Imaging of Materials, from the year 2000, has a relatively short, condensed presentation. It's not that much. It's about 4 or 5 cages to come to a point where you can say, no, I can put it on the computer and calculate myself. Of course, this is extremely short, and you will not be able to do that right away. But if you then read up with that knowledge, you can do that. You can sit down and write complicated computer programs that allow you to calculate complicated spaces. Other questions? Okay, now let's have some tea and take a break. field, and if the molecule rotates, the internuclear vector between the two hydrogens rotates, and the interaction scales with that rotation angle beta. And it scales with the second Legendre polynomial. That's this function here. So that means also that the NMR frequency which we observe depends on the orientation of the internuclear vector in the magnetic field. Or you may say it depends on the orientation of the molecule in the magnetic field. The crystal in the magnetic field. And that means when you have a powder, you will see many splittings. And you will see splitting that follow a particular distribution. And now we have to go back to the case of the orientation of the coupling sensor in the magnetic field. And we know that the NMR frequency is, I had this rotational ellipsoid that's plotted in here. This is the coupling tensor I present here with the x, y, z, and that is parallel to the magnetic field. And this is the coupling tensor. And the angle beta is that angle. And that defines the NMR frequency according to the equation over there, to the second Legendre polynomial, and that is the orientation of the interaction tensor. Now the question is, if this is the orientation dependence of the NMR frequency, and I count in an isotropic powder how many angles beta are there, the probability of finding a molecule at an orientation with the internuclear vector being at an angle beta with respect to the magnetic field. Where do I find more molecules? With the angle beta 0 degrees, or with beta equals 90 degrees? Well, think about it.
0 degrees.
0 degrees means the molecule, the internuclear vector is aligned perfectly aligned with the magnetic field. 90 degrees means perpendicular. And perpendicular, I have all orientations on the circle. So you want to revise your answer? So if I have one orientation perfectly parallel, but all the orientations perpendicular could be anywhere in the plane perpendicular to the magnetic field, then I would have more orientations perpendicular to the magnetic field than exactly parallel. So there will be a higher probability of finding molecules that have their internuclear vector perpendicular to the axis of the field. And that then gives a distribution of NMR frequencies in an isotropic powder for one transition, which has this NMR frequency that shows that funny shape. So at 90 degrees, we have a high probability of finding many molecules there, and at 90 degrees, we have a low probability of finding molecules. And the resulting distribution, or NMR signal, or frequency distribution that we find for an isotropic distribution, that means in a sphere, the internuclear vectors come out at all elements of the surface with equal probability, then gives us this distribution of the NMR signal. So instead of one sharp line, we have a particular line shape. For dipolar coupled spins, we have two transitions. The line splits. So one, and the second transition has a -3 cosine squared beta -1. So it's a blue transition. So the two transitions we find for the dipolar coupled spins are the blue and the red one. And the sum of the signal is what we finally observe and record on the NMR spectrometer if we measure the spectrum. And this is the sum spectrum that results from it. A very funny shape. By no means anything that we observe easily in liquids. We could observe it in certain cases in partially oriented liquids. That spectrum, type of spectrum, is called the PEG spectrum. It's measured for any spin system that has a coupling tensor which has zero isotropy, zero isotropic contribution, and in particular zero asymmetry. If we have an asymmetric powder pattern, it looks different. So if the coupling tensor, like for the nuclear quadrupole interaction, which is asymmetric, or for the chemical shift interaction, which is also asymmetric, we would observe a different, what we say, powder pattern. Now that is called wide line NMR spectroscopy, because if you look at, if you plot the chemical shift scale underneath, that the frequency range, or the frequency range, instead of being, let's say, 2 kilohertz or maybe 10 kilohertz, it can be 100 kilohertz. So it's very wide. The liquid state NMR spectrum will only cover a small range underneath. So this is a very wide spectrum, and this is typical for solid-state NMR spectra, that your frequency range is very large. Which means, on the other hand, if your spectrum is very wide, your signal in the time domain decays in very short times. So the typical decay then is within microseconds or milliseconds for a solid-state NMR signal, the free induction decay that you observe, while in the liquid state case it is in the seconds range. It could be 100 milliseconds to 10 seconds, depending on what nucleus, etc. So we look at very, very different timescales. And that actually also explains why for liquid state NMR we have different spectrometers than for solid state NMR. For solid state NMR, you have much higher demands on short dead time of the receiver because your signal decays so fast. But the question is, what do we learn if we observe such spectra? Well, there is one thing that maybe I should also mention. If you, there's a particular angle at which the offset frequency is zero, at which the anisotropy is zero. And that is when you set omega plus equal to 0, you get beta at the a value of beta of 54.7 degrees when you solve the equation. And that is called the magic angle. That is the angle at which the second Legendre normal goes to 0. And then both resonances at that angle appear at the same frequency. That's exactly the frequency 0 here, because I've only plotted omega plus and omega minus on this axis. So both transitions will appear at the same frequency and overlap. You will not see any effect of the line splitting, nor will you see any effect of the anisotropy. So the line splitting goes to 0, and it means that at that angle, your signal appears like the signal of a liquid. If you would be able to align all the internuclear vectors along the magic angle of 54.7 degrees. Now there's a way of doing that, and that's called magic angle spin. So instead of rotating, averaging out this line shape, so on average the whole frequency dependence vanishes by rapid molecular motion of each molecule individually, you find one particular way of rotating the complete sample so that this disappears. And that is called magic angle spinning, and we'll go to that, but however only after we have looked at how we can make use of the shape of the wide line spectrum. And there are two examples I want to show you. One concerns the, let's say, the solid state, chemical shift anisotropy of carbon-13 in a particular polymer. This is a photo-sensitive liquid crystalline polymer. So there's the main chain, a very large molecule. It has side chains, and these ends over here are photoactive. So when you irradiate them with photons, they switch their conformation. It's nice because it's an intelligent polymer, and it's actually a study that's relatively old. But one of the groups here has been labeled with C13. So some chemists spend a year or a PhD thesis to put lots of carbon-13s in there, which is hard work from the chemical synthesis. And then you can observe a C13 enriched solid-state NMR signal. Now, what you see here are powder patterns of that chemical shift and isotropy. So protons have been decoupled, and you see the line shape, which is kind of reminiscent of one of the wings in the spectrum that I've shown you before. You know, that forms the Peck diagram. And it results because the whole polymer has been oriented in a magnetic field. And so because it's a liquid crystalline polymer, you can then, above the transition temperature on a certain temperature range, the molecules will align in the magnetic field and will become oriented, like liquid crystals do. So also polymers on the side chains of the polymer do. And then you get that type of line shape. Now when you rotate the whole sample, it's like rotating the crystal, now rotating the liquid crystal, which has only partial, incomplete alignment, then that shape changes. The shape of the powder pattern changes. So you can see that it is a distribution so it's a partially oriented sample, and one can do a line shape analysis. Now you go to the computer and you model, how do I get that line shape? What distribution of carbon chemical shift tensors do I need to put in order to get that line shape? Again, it's something that requires a lot of computer programming, but what do you get? You get the distribution of alignments of the chemical groups in that liquid crystalline polymer. You get the orientational distribution function. How well are these groups aligned? Which is very important, because molecular orientation is very important when you do, let's say, produce fibers by fiber spinning. You extrude macromolecules through, let's say, a shower head and pull them out and try to align them. The better you align them, the better is the strength of your fiber. You can do that by X-ray diffraction studies, XRD. But then you can only measure very good alignment, very high alignment, perfect alignment. You get good results. If you have weak alignment, you have problems. For weak alignment, such a line shape analysis is very beautiful, because then you can learn about weak alignment, small deviations from isotropic distributions. So NMR in that sense is complementary to X-ray diffraction. It measures weak orientation. X-ray diffraction measures nearly perfect orientation. So these are complementary methods, and the method of choice is wide line NMR spectroscopy. And here you see what happens when you shine light on this chemical group here, then the total orientational distribution changes. So for that orientation after light irradiation, you get a different powder pattern. And from the powder pattern, you can learn how the alignment of the chemical groups has changed. So one thing you learn from wide line spectra is molecular orientation and the orientational distribution. And the second one can learn is, now in this case, I go to deuterium wide line spectrum. The deuteron has a spin 1, sort of like the pair of two hydrogen atoms. That's also spin 1/2, to spin 1/2. The total spin is spin 1. So you have a similar relationship. You have also get the wide line spectra that looks kind of like the Peck diagram I showed before with washed out wings. And these are simulations now for deuterons sitting either in the methyl group, 3 deuterons on the carbon sits with a chemical bond on some molecule, and what happens when temperature kicks in? It rotates. But the question is, how does it rotate? Does one hydrogen jump to the position of the next one? Are those 120-degree jumps? Or is it rotational diffusion that you progress in small angles? Which mechanism is it? It's very important if you want to make impact-resistant polymers. Then you need to know about the motion of the chemical groups, because the chemical groups that move can absorb the impact energy, and so it's of great technical relevance. NMR, next to dielectric relaxation, is one of the methods of choice. And what people have simulated here is deuteron NMR wide line spectra for different motions, for the jump of a para-phenylene ring, or the triple jump of a phenylene group, or the isotropic rotational diffusion of the phenylene ring. So if you look at the isotropic rotational diffusion of a methyl group, so here those two are methyl groups. One is the jump and one is the rotational diffusion. And you see the spectra differ. And the time scale that's given here is the correlation time of molecular motion. It's roughly the time scale on which these jumps or diffusional steps happen. And you see that the spectra look quite different, which means you can study by wide line NMR spectroscopy the mechanism and the time scale of molecular motion. Again, a very important information, especially in polymer science and material science, where you want to know about the timescales and the mechanisms and the geometries of motional mechanisms on the slow timescale. Okay, so let's move on. We will skip the solid echo pulse sequences, and we will move to magic angle spinning. So I mentioned that if you don't have temperature to introduce isotropic motion to your molecules, you may find some clever tricks that pretend or that make the NMR measurement appear like as if you had isotropic motion. And that turns out that you rotate your sample if you have a first order, let's say, weak interactions compared to the Zeeman field. It appears that means you rotate your sample in a little turbine which is oriented at the magic angle of 54.7 degrees with respect to the magnetic field, which is exactly the angle at which the second Legendre polynomial disappears. Because by doing this, all interactions get scaled with the second length Legendre polynomial. The fact of doing that experiment means that your NMR signal is multiplied with the second Legendre polynomial, and if you set the axis to the magic angle, then these anisotropic interactions disappear. And the beauty of this is that a spectrum which is, again, a carbon-13 spectrum, eliminating protons from the proton coupling by a proton decoupling, that the carbon chemical shift anisotropy of polypropylene with 3 carbons in there in the repeat unit, 1, 2, 3, looks like this. Badly resolved. Chemical shift anisotropy. When you start spinning, suddenly that powder pattern of 3 different chemical shifts breaks down into side bands. So you get lots of peaks. If you spin faster, you're left with 3 peaks only. And these 3 peaks are the peaks that correspond to the 3 different chemical shifts of your carbons in the spectrum. And now you have a high resolution spectrum. What you would expect when you have a polypropylene melt or polypropylene at high temperatures in the molten state where there's rapid motion. But that you can measure at room temperature. And these side bands actually appear as offsets from the center band at the rotation frequency. So these little dips here mark where the side bands are at the frequency separation, not the chemical shift. The frequency separation is exactly the spinning speed. I should mention these spectra were measured 30 years ago when people couldn't spin very fast. 6 kilohertz spinning speed was something big. Today you can buy spectrometers that have 100 kilohertz spinning speed. So it means 100,000 rotations per second of a mechanical device, which is incredibly high. And so the spinners are very small. They can be 1 millimeter outer diameter, that's this much. And there's a hole inside and a cap on top, and you put your power into the hole and the cap on top and everything that you put into the magnet, and you start spinning it with a gas-driven turbine. Very sophisticated, very complicated, difficult to do. It goes back to the very first lecture. You need an expert to do these experiments. But when you do them, you get high-resolution spectra, and you can do beautiful high-resolution NMR spectroscopy as you can do from liquids. So, there are a couple of tricks involved in solid-state NMR spectroscopy. And those tricks, because you want to usually do carbon-13 spectroscopy with magic angle spinning. If you do protons, then the dipole-dipole interaction is so strong that it's still not quite possible to eliminate the dipole-dipole interaction. You may do with these ultra-fast spinning speeds, you may eliminate the dipole-dipole interaction, but classically one does carbon-13 NMR spectroscopy. You spin fast enough to eliminate the anisotropy of the chemical shift. because that's narrow, there's a smaller bandwidth, you need slower spinning speed to eliminate that. And carbon-13 has a disadvantage of low abundance, low sensitivity, and long relaxation times T1, which means you have to wait 5 T1 before you can rebuild, before you can start your next experiment for signal averaging. So you want to have short T1 and you want to have high signal on the carbon-13. How do you get high signal? You get the magnetization from the protons and transfer it to the carbons. And that transfer step is called cross-polarization. That's shown here. You do a 90-degree pulse on the carbons, you tip the magnetization on the protons, you tip the magnetization from the protons into the transverse plane, and then you flip, your B1 field is in the direction perpendicular. So that's the B1 field, and that rotates the magnetization over in the transverse plane. And then you flip your B1 field so that it's aligned with the spin, with your magnetization. So your B1 field, after that, at this stage over here, for the cross-polarization, is aligned with the direction that your magnetization points to. And all the spins now precess in the rotating frame around the B1 field. They rotate. We say that it's a nutation. That is not called precession anymore, it's called nutation because it's in the presence of the radio frequency field. And you do the same thing for the hydrogen, but you also do it for carbon. So you have a magnetic field in the rotating frame, in each case, where the spins rotate precess around the B1 field. Now you can do one thing. You can make that precession frequency, or nutation frequency, which is given by the strength of the B1 field times the gyromagnetic ratio, you can make that precession frequency the same for hydrogens as for carbons. Now you have two systems that have the same resonance frequency, the same frequency, and they couple through the dipole-dipole interaction. So what happens when you have coupling? You have two systems resonate with the resonance frequencies at the same frequency. They couple and you have transfer energy from one system to the other, and you couple it back. You probably all have done the experiment that coupled pendulums in elementary physics, and one oscillates and the other one oscillates, and then you transfer the energy back and forth between the two. That's what you can do now when you have established that resonance condition and moving energy from hydrogens to carbons, and it moves back to hydrogens, etc. So there's we call a cross-polarization time, which one can adjust to move the energy or the polarization, the magnetization, from hydrogens to carbons. And that has the advantage then that you can get higher signal on the carbon channel, and has the advantage that you only have to wait 5 T1 for the protons, which is shorter than 5 T1s for the carbons. You can accelerate, do your experiments much faster. Was invented by Alex Pines, was one of his first experiments that he found, very famous, I think it was 1972, and it's cross-polarization. No, this was Hartmann and Hahn. Oh, I mixed it up. This is the Hartmann-Hahn experiment. This is the Hartmann-Hahn condition. Where are we? Yeah, so the matching of these resonance frequencies is Hartmann-Hahn condition. This is when omega 1H equals omega 1C, and then you use dipolar decoupling, that is irradiate the protons while you detect the carbons in order to get your C13 NMR signal. Okay, so I should probably move on to the last short topic before we finish for today. And I've shown you the magic angle spinning, how we narrow the lines by moving your sample physically in space to the magic angle and rotating around it. And we've also seen that you can enhance the signal by cross-polarization, magic angle spinning. And in this way get higher signal, the signal from the protons, and shorter waiting times between scans, because the relaxation time of the protons is important to build up magnetization, which is then transferred to carbons. Now there's another way of eliminating the dipole-dipole interaction. And this is kind of clever, because the Hamilton operator, you know, this magic energy operator which we had before in the course this morning, that consists of a part that is depends on the space coordinates, which allows us to magic angle spinning. We make that 0, and the dipole coupling disappears. And the other idea is we can work with the spins and say, let's move the spins to the magic angle on the time average. And that you do by radio frequency pulses. So no physical spinning of the sample, but only manipulating of spins so that on the time average that are elongated along the magic angle. And that is called multi-pulse spectroscopy. And the beauty of the magic angle is that it is actually the angle that you have when you draw the diagonal on a cube to one of the sides of the cube. That is the magic angle. So what you need to do is that you put the z-axis of your interaction Hamiltonian along the x-axis, along the y-axis, and along the z-axis. That is your x, y, and z axes of your coordinate system that defines your Hamiltonian. You have to rotate them in such a way that they're equal times along the direction of the magnetic field. And this you can do with a simple pulse sequence of 4 pulses, which is called Warhuber Haberlin are the inventors of this. And you find that your z-axis, let's say initially, is of your coordinate system where the Hamiltonian is defined, called the toggling frame, is along the parallel to the field, and then you do 90-degree x pulse, and now you can apply your right-hand rule, and we'll find that then the y-axis is along the z-axis, and you do a minus y pulse, and the x-axis along the z-axis along the magnetic field, and then another plus y pulse, and which moves the y-axis again to the direction of the field, and then a minus x pulse, which moves the z-axis again. And you count how often, for how long are the different axes along the direction of the magnetic field. You find this is for a time tau, and therefore time tau, so a total of 2 tau. Here we are for a time tau, there we are for a time tau, it's also 2 tau, and this is 2 tau. So for a time 2 tau, each of the axes where your Hamiltonian operator is defined in is along the direction of the magnetic field. On the time average, it's oriented along the diagonal of the cube, and it is the magic angle with respect to the magnetic field, and the interaction Hamiltonian vanishes. Again, it's a pictorial interpretation, which shows you it's important to know that the magic angle is the angle away from the axis of the cube to the diagonal. And you can play with the spins by pulses that then exploit that so that the interaction Hamiltonian of the dipole-dipole interaction disappears. And this is called multi-pulse spectroscopy. It is important when you don't have spectrometers that allow you to do fast magic angle spinning. You can do magic angle spinning and multi-pulse spectroscopy together to get high resolution or sort of higher resolution NMR spectra even in protons. And that brings me to the end of solid state NMR spectroscopy. We'll revisit solid state NMR spectroscopy in the context of two-dimensional NMR tomorrow. And we will see two-dimensional solid state NMR spectroscopy exploiting, for example, the quadrupole coupling of the deuteron, which gives rise to two transitions and the peg pattern, as we have seen for the dipole-dipole interaction. So for today, I want to stop here because there are other obligations that I have to be really on time. And I'll see you then tomorrow, and we will move on to liquid state, two-dimensional NMR spectroscopy, and also some solid state, two-dimensional NMR spectroscopy. So if you have any questions, please ask.
I don't understand how Hamiltonian interactions move by magic angle spinning.
How the Hamiltonian is changed by magic angle spinning, that requires a lot of math. Essentially, your whole interaction is multiplied with the second neuronal polygon. So instead of just having the Hamiltonian or the transverse magnetization that results from it, it is multiplied now with the second Legendre polynomial, and that means, and the second Legendre polynomial has the angle away from the magnetic field. And if you set that angle or the angle of the rotor, of the magic angle spinning rotor with respect to the magnetic field. So by setting that angle to 54.7 degrees, your whole interaction Hamiltonian disappears. But you have to run through all these equations to see how that happens. But the net effect is the multiplication of your expression for the magnetization with the second Legendre polynomial involving the orientation angle of the rotor with respect to the field.
So it is mathematically, we can say.
Yes, you have to work through the math, and it's a pretty complicated set of equations that you have to run through. And
if we understand physically, how can we understand?
Well, the physical interpretation is essentially that all the interaction tensors, or let's say all the spins, all the different magnetization components talking to each other, are aligned along the magic angle, and the interaction energy and the interaction and the line splittings resulting from them scale with the second Legendre polynomial. And the second Legendre polynomial is 0 at the magic angle. That's a, let's say, an approximative physical picture for it. So essentially, you take the most simple geometry or most simple motion of molecules that allows you to set the interaction to 0. And it is not the most general geometry of having isotropic molecular motion, but only motion around the magic angle. Because we only have a second rank tensor to average to 0. Which second rank tensor is the interaction tensor for the different types of interactions. Not happy. Yeah, so the physical picture is you want to mimic the molecular motion you have in liquid. And you want to find the simplest motion, not the most general ones, as isotropic motion in liquid does, that allows you to average to 0 your interaction. And the simplest motion is just a motion around the magic angle. That's all you need. You don't need isotropic. Bit happy? Okay, other questions?
Sir, what would happen to the NMR spectra if we use tritium instead of protein?
If I lose
Tritium.
tritium,
Yes.
tritium has a spin 1/2. Yeah. Same thing. You have a different chemical. No, you don't. You even have the same chemical charge, right? It's just more sensitive. You have a higher NMR frequency. That's all. And of course, it's short-lived because it's radioactive.
We would have a sharp spectra in comparison to protein spectra.
It depends on the state of your tritium. If it's in a liquid, then you would get narrow lines. If it's in a solid, you get wide lines. So it really depends on the molecular motion, the mobility. The higher the viscosity, the lower the molecular mobility, the wider the lines will be, until you reach the rigid lattice limit, and you have the sort of dipole-dipole interaction between the different tritiums, and that gives you the wide spectrum of maybe 100 or 120 kilohertz. So similar to what you expect in protons.
So one more question.
Yeah.
So you are telling about the we can spin nowadays at 100 kilohertz.
Yes.
So how can we spin increase the spin?
Oh, then the wall of your rotor goes beyond the speed of sound. Okay, and that makes it very difficult. So you can use different gases to drive your spinner turbine to increase that, and you can use smaller spinners. But of course, you're already down to a milliliter. How small can you get? And the other thing to worry about then is the strength of your housing where you put your sample in. I mean, these are ceramic materials, and very special ceramic materials that have very high strength. With the dried gases and the physical environment, I guess that you can check. But I wonder if you can get much faster. I guess people have even moved to a few frequencies, a few kilohertz above 100 to maybe 120. Yeah. But I don't see how it can get faster. Maybe you have a concept how to do that.
So then precession frequency also changes. Precession frequency.
Oh, the spins still are locked to the magnetic field. They don't see the rotation of the molecules. They are locked to the magnetic field. That's the whole concept. Right? The spins are locked to the field and the molecules rotate. And that is sort of what then mimics the motion of the isotropic motion of the liquid. You know, the spins always stay aligned to the field. And the molecules in which they sit, they rotate. And that means the interaction, the coupling of the spins to the other spins or to the molecular, to the electronic environment, that spins, and it rotates with the rotation frequency of your molecule.
How the tumbling
Yes.
of molecules,
Yes.
It affects the peaks. They get narrower or broader.
Yes. Yes.
How?
Essentially, it is a relaxation time. It's the decay time of your impulse response or free induction decay signal. And there are theories that the molecular motion is the Larmor frequency, twice the Larmor frequency, and near frequency 0 affect the relaxation times T1 and T2 in different ways. And depending what the spectral density of motion is at these frequencies, then that determines the T1 and T2 relaxation times, and that determines the T2 relaxation time determines how broad your NMR signal is. Whether it's narrow, when you have a long T2 relaxation.
If interactions are more, then they get broader.
Say again?
Interaction.
If the interaction is strong, well, it depends on the frequency of the interaction. It's a dynamic process. It's a time scale of the interaction. So you have to Fourier transform the time course of your random motions, and then you get the spectral density, or do the autocorrelation function of your random motion, and then do the Fourier transform, then you get the spectral density, and you look how that overlaps with your NMR frequencies. And that allows you then to estimate if they get broader or But in the end, it's the impact of molecular motion on T2. That's why also in solids we have these large lines, because T2 gets very short through the dipole-dipole interaction. You're getting nervous.
And now we have to move another building, Guru Sapan, go to the main road and then to the right, the next building to Guru Sapan. We have here at 11 o'clock sharp. And in the afternoon, 10 students will go to the spectrometer. So Anu will coordinate. You will come here?
I don't know.
Who will coordinate? You can have this shoot the given just take your work. So you reach there at 2:10.